Okay, so this second video is a collection of demos regarding electromagnetic induction. And so in chapter 19, we learned about magnetism, and we also learned that an electric current can produce magnetism. In chapter 20, we learned about Michael Faraday's discovery, which is that magnetism can in turn produce electricity. And that's what we mean by electromagnetic induction. So the demos today all have something to do with electromagnetic induction. Okay, so let's begin with our first demonstration, which uses a galvanometer and a coil. As you remember from chapter 19, the technical name for a coil is a solenoid. So here's the solenoid. It has about 1,000 turns. It's using enameled magnet wire. You've probably seen something similar in guitar pickups. That's the science behind guitar pickups, is they use electromagnetic induction to amplify sound. So here's the coil, and then it's connected with these alligator clips to a galvanometer. Now, you guys in chapters 17 and 18 used multimeters, which you could set to measure voltage or resistance or current. When something measures current, it's called an ammeter. Now, a galvanometer is somewhat similar to an ammeter. A galvanometer does measure small currents. It can only measure direct current, not alternating. Its advantage is that it shows you both the magnitude and direction of the current, whereas an ammeter only shows you magnitude. But again, this is just for very small currents. So the galvanometer is a great instrument for showing us electromagnetic induction in action. Okay, so I have this little bar magnet here. I've got the North and South Pole. And what Faraday discovered is that if you have a coil and you move a magnet through it, you get a tiny current. Okay, so watch what happens when I introduce the bar magnet into the center of the solenoid. Keep your eyes on the galvanometer. You see that deflection? Let's look at that again. Deflection, and then if I pull it out, deflection in the other way. All right, so let's do that again. North pole's going in, increase of flux, okay? And I get that deflection going one way, which means there's a negative current. And then when I do a decrease of flux, I get a positive current. Let's see that one more time. Increase of flux, negative current. Decrease of flux, positive current. And this is how we see Faraday's law in action, okay? Because notice, the current is only induced while the magnetic flux is changing. When it's not changing, there's no current, okay? So if I put it in, I get the deflection, but then the galvanometer goes back to zero, because if I keep the magnet there, there's no change in flux. But then if I pull the magnet out, there's going to be a sudden decrease in flux, and that's why I get the deflection in the opposite way. So Faraday's law is that the EMF equals negative N delta phi over delta T. We see the negative in action because an increase in flux, which is a positive delta phi, leads to a negative current. That's the negative. A decrease in flux, which is a negative delta phi, leads to a positive current because the negative of a negative is a positive. Okay, so that's the negative in action. The N is the number of turns. That's about 1,000 on this one. So N refers to that. The delta phi over delta T is how fast the flux is changing per unit of time. Okay, so watch, if I do this really slowly, I get very little effect. And if I pull it out very slowly, I get very little effect. Because, yes, the flux is changing, but the flux is changing very slowly. And so the magnitude of delta phi over delta t is low. But if I do it quickly, notice how much that was. Delta phi over delta t was high. And now if I bring the magnet and suddenly increase the flux, watch what happens to the needle. It deflected a lot. Sudden decrease, sudden increase, sudden decrease, sudden increase. Okay? So that's Faraday's law, and it's actually a profound discovery because the use of magnetism to produce electricity is responsible for all the electricity that we use every day, because that's how generators work. Okay, we're now going to look at another example of electromagnetic induction. But to show you this, I'm going to have to turn off the lights. All right, luckily there's still enough daylight coming in so you can see what I'm explaining. This is a very simple DIY flashlight. Now, it doesn't produce a steady beam like a regular flashlight, but I want to just show you how it works because it illustrates electromagnetic induction. What I have inside, this is just a plastic straw, a hollow section of plastic straw. And then these are neodymium magnets, pretty strong permanent magnets. And then there's magnet wire, many turns. I think this is about 300 turns. And then I connect the magnet wire with electrical tape to the two terminals of an LED. Now, let's talk about the principle here. If this magnet is going back and forth through the coil, that means that there is going to be a constantly changing magnetic flux through the coil. And as we know from Faraday's law, we should get a small current. So if I shake this back and forth, shake the magnet back and forth, then we should be able to see the LED light up. Okay, so I'm just gonna hold it like this, make sure the connections are solid, put my other fingers to keep the magnet from shaking out, and then now watch. Did you see the light? You can see the light, and notice that, like I said, it's not a steady beam. It's not supposed to be. But you should see some blue flashes. I'm seeing blue flashes from where I am. You may have to, I don't know, do slow-mo on the video or pause it or something like that. But I'm definitely seeing blue flashes. And I'm gonna do it a few more times for you. Yeah, I saw it right there. And I think, at least what I'm seeing on the camera, is that some of those flashes are showing up. Interesting thing is that those little flashes, each one of those little flashes doesn't come from a battery. It doesn't come from any other source except the action of my hand shaking the magnet so that there's a constantly changing flux through the coil. Now, you've probably all seen shake flashlights before. This is a manufactured shake flashlight. It does give you a steady beam because what happens is as you shake it, you charge a capacitor, and then the capacitor supplies the bulb, which is usually an easily lit LED. All right, so notice that I'm going to put it up close here. You can see the coil. That's the copper wire there, and then see the inside. If you look closely, you'll see something kind of going down, going up and down, back and forth as I'm tilting it. That's the magnet. So it's the same principle as the little straw that I showed you. But with the capacitor, we're gonna get the steady light. So first let's charge it. And we charge it just by simply shaking it back and forth. As I'm shaking it, notice I'm doing constantly changing flux. constantly changing flux. And that constantly changing flux charges the capacitor, and I've got light. It's pretty neat. No batteries, nothing, just manual power. So it's a good emergency type flashlight to have. All right, next thing is a kind of a miniature windmill. So all it is a little propeller attached to a DC motor. And you can see the way the gear ratio is, right? The big gear is attached to the propeller. The small gear is attached to the motor. So that's a better view. You can see the small gear that's on the motor, the big gear that's on the propeller. And so for only a few revolutions of the propeller, we get many revolutions of the motor. Now that's a DC motor. If you input electricity, you get mechanical rotation. But if you input mechanical rotation, you get electricity. That's electromagnetic induction at work. And you should be able to see this light up the LED right here. There, yeah, so I'm just, of course, using my hands to turn the propeller. But if I, hooked up a blow dryer here, or some powerful source of wind, I would be able to see this light steadily. And if I hook this up to a very large propeller, capable of harnessing large amounts of wind, I could get a steady light. But it is pretty cool how this renewable energy, right, it's just wind or just mechanical input, gives you electrical output. Okay, we're going to look at another generator. This is a hand crank generator. And the hand crank generator is built on the same principle. We can see the gear ratio is interesting. Look at the cascading of gears. Okay, so the crank is attached to that first big gear, but then that big gear meshes with a small gear, and then that small gear is itself attached to a big gear, and then that last big gear meshes with the small gear of the motor. And so we have a multiplication of RPMs. For only a few RPMs of my hand, I get many RPMs of the motor, which is here acting as a generator. I'm kind of doing that slowly for you to see those gears in action. Okay, that's called cascading. And when you cascade gears for an increase in RPMs, that's called gearing up. So this is geared up, and here's what I've attached it to, just a little flashlight bulb in a bulb holder. And so you can watch while I turn it, I'm getting light. Now, it's hard to get a steady light because it's hard to have perfect uniformity with the turning of my hands, but I can approximate it. Also notice that the faster I turn, the brighter it burns. The slower I turn, the dimmer it burns. Faster, brighter, slower, dimmer. Now, if I take the load off this generator, so let's just disconnect. I disconnect it now. Well, this becomes very easy to turn. Super easy to turn. You can even hear a slight difference in the sound. It's slightly higher pitched. It's very easy to turn. But once I connect it back to the load, back to the thing that uses the electricity, it becomes significantly harder to turn. And you can even kind of hear that in the sound. See, it takes some work. It takes some work to turn that crank. And if I did this for an hour, my arm would be tired. All right, but anyway, that's the hand crank generator. It's really neat. It's a good model of the generators that produce our household electricity. Okay, we're gonna keep doing these things with the lights off because this next thing is really cool. This is called a plasma ball. And I'll turn it on and then I'll kind of explain what's going on. Okay, so you've probably seen something like this before. Step aside a little bit so you can see it better. The dark background's better, so I'll keep it like that. Okay, so plasma is the fourth state of matter. It most closely resembles gas, even though it's not exactly gas. Well, actually, it's not gas. So, as you know, the three normal states are solid, liquid, and gas. Plasma is different from gas because in gas, what you have is you have mostly neutral molecules, like oxygen molecules, hydrogen molecules, whatever the gas is. But in a plasma, what you have is a hot mixture of freely roaming electrons and positive ions. And so even though as a whole the plasma might be electrically neutral, every single part of the plasma is charged, and so plasma is an excellent conductor of electricity. So what we're seeing here is we have a high voltage alternating current coil in the middle. It's called a Tesla coil. And what it's doing is it's making the noble gases that are contained in here, it's turning those noble gases into plasma. And then since it's creating a current, the current is traveling through the plasma, since plasma is now a good conductor of electricity. And then it's discharging into the air. Now look at this interesting thing. If I touch it, notice that it wants to go to where my finger is. You can see it's going to where my finger is. If I put my palm on it, notice that everything wants to go to where my palm is. And the reason that happens is because even though our bodies are not great conductors of electricity, they're still better conductors than glass. And so since we make contact with the glass here, it's easier for those electrons to jump through the glass into the decent conductor that is my finger, and you can see the result. See what happens. I'm going to hold it a tiny bit closer so you can see that. Okay, you can see how it's going towards the finger when the finger is when I touch the plasma ball. And then that current just goes through my body and into the ground. Another interesting thing about the plasma ball is that it's an easy way to ionize gases in other containers, such as this long fluorescent bulb that I found. Long fluorescent bulb. Okay, it's very long. It's like, I think it's about 6 feet or so long. Now, notice what happens when I touch it to the plasma ball. See, it lights up. It lights up. Hopefully you can see that. I did turn off the lights, and I can see the light pretty well here when the bulb lights up, but I'm not sure how well that's transmitted through the video. So what's happening is that plasma is transferring electrical charge into the gas contained in the bulb, moving or exciting its electrons to higher orbitals, and then when they come back down, they release photons. But notice how I can make the whole bulb glow. See, I'm making the whole bulb glow. But also notice how the glow ends at my hand. The glow ends at my hand. There, now it's glowing, but notice that to the right of my hand it's not glowing because at that point it's just going through my body and into the ground. So no glow, glow, no glow, glow. And that's bringing it a little bit closer, just so you can see that difference. Yeah, at least you can see the color difference of how it's glowing, but no longer glows past my hand. Now, the reason I brought the plasma ball for this particular demonstration is that I wanted to show you the sound activation. So this plasma ball has a mode where it's sound activated, and while it's sound activated, okay, the main power has been reduced to the Tesla coil, but then the Tesla coil gets jolts of power when a sound is made. And the way this works is through electromagnetic induction. Okay, it's the same principle as a microphone. A microphone takes the vibrations in the air or sound and then moves a magnet through a coil in response to those, and that produces a current that then gets amplified through the speakers. Well, we're going to see something similar here. See, if I clap, you can see it gets quite strong. So no sound, there's not much going on. But with sound, it suddenly gets bright. And I'm going to keep it over here so you can see that a little bit more. Notice now with the sounds that I make, it's going to be getting little jolts of electricity. Did you see that? All of that was because of electromagnetic induction. All right. Now, the next few things I'm going to show you will have the lights on. So let me go turn the lights back on. Okay, the next thing I'm going to show you has to do with Lenz's law. So Lenz's law states that when there is a change in flux, nature which heat changes sets up a magnetic flux that's opposed to the change that caused it. And usually that ends up resulting in a force. Now, if you want a review of the right-hand force rule, you can go to chapter 19 for that. But we know that there's a force on a charge that moves through a magnetic field. So let's look at this little pendulum here. It's just a pendulum made of Legos with a copper electrode or a little copper strip. And we can see that if we, move it like a pendulum, it's just going to go back and forth until friction stops it. See that again. And it kind of slowly comes to a stop at the very end, but there's still like small amounts of motion. Well, if we add some magnets and we set up a magnetic flux through the bottom of this pendulum, okay, the bottom of the pendulum has little arches there that fit the magnets. So let's connect those. Okay, so now what I have is, I have these magnets set up and they're being held in place just by magnetic force, nothing more. And we're going to see what happens when we drop the copper strip through it. Watch. Notice how quickly the motion ends. And at the very end, it doesn't just fizzle out, but comes to a complete stop. You can notice the slowing effect almost immediately, and the slowing effect gets more and more drastic. And the whole thing comes to a stop much more quickly than it does without the magnets. So how does this work? Well, this is something called eddy braking. So look at it this way. This copper contains a lot of charges, obviously, because it's a metal. It's a good conductor. Right now, there's no flux through it. But when the copper goes through the magnetic field at the bottom of the swing, suddenly there's an increase in flux. And nature doesn't like that increase in flux, so it attempts to decrease the flux with eddy currents, little loops of current set up in the copper conductor itself. And the direction of those eddy currents is such that the magnetic field induced by those currents is then in opposition to the magnetic field that caused them in the first place. Okay, so then it comes out, no flux. And notice that every time it goes through, there is a sudden increase in flux. Flux increasing. And then there's a sudden decrease in flux. Flux decreasing. Zero flux, comes back. Flux increasing. Decreasing. Zero flux, and so on. And every time there's that change in flux, Lenz's law tells us that there's going to be some braking going on to oppose that change in flux. And all of that is based on the right-hand force rule. So we already went through the theory of this in chapter 19 and chapter 20. But I'm just showing you the consequences of that theory in this demo. Let's look at another even more interesting consequence. This is a copper tube, and this copper tube has a little window in it. See a little window in it. And if you drop something through it, you should be able to see it fall. Okay, so the first thing I'm going to drop through it is just this little aluminum cylinder. Little aluminum cylinder. Remember, aluminum's not magnetic. And you should be able to see it if you keep your eye on the window there. You should be able to see it slide through. I'll do it again. Did you see it slide through? Okay. Now, if I drop it, so if I drop it through this, and I'm going to hold it here, I'm holding it vertically right now. So watch what happens when I drop, and see how fast it drops. You'll hear the sound of it hitting the table. All right, that's to be expected. It's just something falling, so hits pretty quickly. Let's do that again. And one more time. Notice how quickly it happens. All right, now, if I get another cylinder, which is a neodymium magnet of the same exact shape and dimensions, I want you to watch what happens. I'm gonna hold it vertically again, okay? You can see it in my finger, and you can see when I let it go. So watch, I'm gonna let it go and then see what happens. Did you see how long that took? Again, watch. Okay, haven't let it go yet. But once I let it go, you can even count the seconds yourself, how long it takes for it to hit the table after I let it go. 1001, 1002. That was 2 seconds. It took 2 whole seconds for it to follow through. And it's not because of friction. It's not because of glue. It's just a hollow tube. It's just a hollow tube. And it's just a cylinder that fits inside the tube. But the non-magnetic thing fell right through. I'm going to do that again, so you can see what I mean. Just a second. Okay, so watch my fingers. I let it go, almost instantaneous. Magnet, I let it go, and it takes forever to fall out. The reason for this is eddy braking. It's the same exact principle behind the pendulum that I showed you. So this magnet, when it falls through the copper conductor, induces eddy currents. And it induces eddy currents because we have a constantly changing magnetic flux through the conductor itself. That introduces the force of braking because nature wants to slow down. It wants to slow down the fall of this thing because this fall is causing so much change in flux. This is a perfect example of Lenz's law in action. Now, if you've ever ridden one of those spinning bikes in a gym, they use this principle to add magnetic resistance to the flywheel. So like, you know, you've got a disc, that's the flywheel, and if you look closely next time, this isn't true of all models, but certainly of some, especially the ones that they call spinning bikes. Spinning bike has two magnets like that, and depending on how much this is going over the flywheel, you can get more or less resistance. And all of that is based on eddy current braking, which itself is a consequence of Lenz's law. Okay, just a couple more things to talk about. Well, really just one more thing. Let's talk briefly about transformers. Transformers, not the robots, but transformers in electricity are devices that change voltage. And this is the basic principle of a transformer, okay? You've got the primary coil, which has a certain number of windings, and you have the secondary coil, which has fewer windings, all right? So if you put a certain voltage into the primary coil, if it's an alternating current, well, an alternating current which keeps switching directions through the primary coil means that you're going to get a constantly changing magnetic field inside it. Now that constantly changing magnetic field, right, means that the flux inside the secondary coil is constantly changing. And so that in turn induces a current. So you could have current coming into this, and then you'll have current going out of this. But the power is the same because P equals IV. But what you're getting is, you're getting high voltage in the one that has more turns and low voltage in the one that has fewer turns. That's called a step-down transformer. A step-up transformer does the opposite, where the power input goes in here at low voltage, but then comes out over here at high voltage. So this is how we, the transmission of electricity through power lines takes place at high voltage, but then it has to pass through a step-down transformer to bring it to the 120 volts that you need for your house. Okay, that's the principle behind transformers. And now I'll finish just by showing you a couple transformers. I'm not showing you the insides, but this is just an example. This is a transformer that is used, or was used, to power a security system. The input is 120 volts, probably too small for you to read those letters. Oh, maybe not. I'll hold it up close. Input is 120 volts, and it looks like the output is 16.5 volts. You might be able to see that. So input 120, output 16.5. This is a step-down transformer. Over here, we have a big old heavy-duty step-up transformer. It's called a neon transformer. And this is used to power neon lamps, which require high voltage to, turn that neon into a plasma that glows. Well, it says here that the input is 120 volts, as you'd expect, but the output is 7,500 volts. See if you can, yeah. Input 120, you can see that up there, but the output 7,500 volts. So there's a high voltage transformer. It's quite dangerous, really. It's not something you want to mess around with. All right, and that concludes our video on electromagnetic induction. The next one will be on light and optics.